Yeah.
Let me try to.
Okay, great.
All right, so next we have Bill Fefferman from Chicago, who will be telling us about noise versus imprecision and the hardness of random quantum circuits.
Okay, great. Thanks so much for the introduction. So it's great to be here virtually today to tell you about the hardness of random circuits. This work will be based on two joint works with my Berkeley colleagues. The first is based on joint work with Adam Boland, Chinmay Nurki, and Umesh Vazirani. And the second paper, which is very recent, is based on joint work with Adam Boland, Zeph Landau, and Yunqiao Liu. And the second paper, just appeared on the archive like a few months ago. So the starting point for this talk, as I think many of us know, is that the first quantum supremacy claims have now been made. We've seen, several of these already, including some in the last few weeks. But the first one was by Google in late 2019, who implemented the random circuit sampling proposal on 53 qubit 53 superconducting qubits. And then more recently by a quantum optics group at USTC who implemented the Gaussian boson sampling proposal in late 2020. So in this talk, we'll give the latest complexity theoretic evidence to believe that these experiments might be solving hard problems for classical computers. So we won't settle all of the problems, but we'll sort of get as far as we can, okay? And I'll kind of bring you up to the frontier of what's known and what's not known. So from a physical point of view, these two experiments are completely different, right? That is, roughly speaking, what constitutes a qubit or a quantum gate is completely separate, but they have a shared theoretical framework. They're both solving random quantum circuit sampling problems. In other words, the hard problem is to sample from the output distribution of a randomly chosen quantum circuit drawn from some distribution, okay, which we'll describe in a moment. So the initial theory goal, which has been a goal for almost 10, probably more than 10 years now, and still has not been resolved, is to prove the impossibility of an efficient classical sampler algorithm that's a classical algorithm that essentially tries to simulate an idealized version of the quantum experiment. So what that means is it should be given as input a description of a random circuit C with an output distribution D sub C, that's if we measure all the qubits, right? And then the classical algorithm, given this circuit description, should output a sample from any distribution X that's close in total variation distance to D sub C with high probability over the choice of C. Okay, so we're trying to show that no such classical sampler algorithm can exist to sample the output distribution of a random quantum circuit. That's the goal. So let me now describe what Google's ensemble of random quantum circuits, to say what we mean when we say a random quantum circuit. So what they do is they generate a quantum circuit C on n qubits on a 2D lattice with around square root n layers of Haar random nearest neighbor gates. So each layer might look something like this. The circles are qubits. The edges here are Haar random 2 qubit nearest neighbor gates. Well, this is a single layer. The next layer could look different. For example, we could connect horizontal neighbors with our gates instead of vertical neighbors. What we do is we start with the all zero input state on all the qubits. We apply, these square root n layers of our random quantum circuit, and then we measure all n qubits in the computational basis to get a sample from the random circuit. Okay, so how do we prove that this sampling problem is hard for a classical computer? Well, we can't do it yet, but all of our current methods start in the same place, which is we first make use of well-known reductions that were due first to Stockmeyer in the mid-80s, which say that if our goal is to prove the hardness of sampling from a random circuit, then it suffices to show that giving a certain additive estimate to the output probability of a random quantum circuit is sharp P hard. Okay, it's a hard problem. So graphically, we think of Stockmeyer's reduction as working as part of a proof by contradiction. It sort of works as follows. It says, let's say for the sake of contradiction, there does exist a classical algorithm that samples from the output distribution of most random quantum circuits. Well, then there's another algorithm. And what this other algorithm does is it uses an NP oracle. So strictly speaking, it's not an efficient algorithm, but it sort of computes output probabilities in this non-standard sense. In other words, giving a certain additive estimate to the output probability of most random quantum circuits. So our goal is to show that this problem is sharp P hard, this problem on the right, this estimation problem, which would then say that it's very unlikely, unless the pH collapses, that there should be an NP algorithm, an algorithm that uses an NP oracle to solve this problem. And therefore, because of Stockmeyer's reduction, there cannot be a classical sampling algorithm. Okay, so before I go on, let me just make it stop for briefly and ask if there's any questions about the basic framework of what we're trying to do. Okay, cool. So let me then go on. Let's make this conversation a little bit more precise. So I'll start with a really simple definition. I'll call the output probability of a quantum circuit this quantity. It's just simply the probability if we start in all zeros, we apply our random circuit, and then it's the probability that when we measure all n qubits in the computational basis, we see all zeros again. All right, so that's P0 of C, and we'll stick with this notation throughout the talk. Okay, now the main subject of study in this talk will be what I call the delta random circuit estimation problem, which is given as input a circuit C, output an estimate Q to the output probability P0 of C with imprecision delta with probability 2/3 over the circuit. Okay, so this is just formalizing what I told you about in the last slide. It turns out to prove the goal of hardness of sampling using Stockmeyer's reduction, it suffices to show that the delta equal 1/2 to the n problem is sharp P hard. The reason 1/2 to the n is so important is because for Google's ensemble of random quantum circuits, this is the size of a typical output probability. Okay. Now, we can't show this. We've been trying for the last 10 years, but we've been getting progressively stronger results. So with respect to a circuit C on n qubits, and throughout this talk, I'll think of the size of the circuit as on the order of n times d, where d is the circuit depth. In our original paper on the subject, we were able to show that the delta equal 2 to the minus O of m to the 4th problem was hard. Movisag improved this to 2 to the minus O of m to the 3rd. In very recent work, we've been able to improve this dramatically to 2 to the minus O of m log m, but we're still not where we need to be, which is 2 to the minus n. So now what I'll say is in the case of boson sampling with this, which is this linear optical proposal for quantum supremacy, it turns out that very similar hardness arguments take us even closer to the goal of proving the boson sampling conjectures. So that is with respect to a boson sampling experiment with n photons and m equal n squared modes, in 2011, in their original paper, Aronson and Arkhipov were able to show that the delta equal 1/e to the n to the 4th problem is hard. In our recent paper, we were able to improve this to 1/e to the 6n log n. And now the goal changed, and it changed in our favor. The reason for that is because the size of a typical output probability in a boson sampling experiment is 1/e to the n log n. So, we're only off by a factor of 6 in the exponent after our very recent paper. And it seems so close, especially if, like me, you've been working in this area for 10 years and this is sort of the best we can do now. But we think we've hit a barrier, which is sort of frustrating. In other words, to do essentially any better than what we've done, we think we'll need dramatically new proof techniques. And we'll talk about this more toward the end of the talk. Okay, so let me give a roadmap for the rest of the talk. First, I'll sort of review our result from 2018 and the hardness result. And to do this, we'll first discuss Lipton's average case hardness result for computing the permanent of a random matrix. It's a beautiful result, and it will also serve as a template for our discussion of random circuits. And then we'll adapt Lipton's result from the permanent to the output probability of random quantum circuits. We'll see that in many ways, the permanent of a matrix is a similar sort of mathematical quantity to the output probability of a random circuit. And then we'll show a result from our very recent paper, which proves that these results are robust to uncorrected depolarizing noise in a certain well-defined sense. And this robustness actually will give a barrier against improving our hardness result to larger imprecisions delta. So in other words, as I said before, what we'll show is the fact that we're getting this robustness to sort of uncorrected physical noise will actually tell us that to improve our result to larger imprecisions, we're going to have dramatically new proof techniques. Okay. Let me take questions before I launch into the sort of technical part of the talk. Okay, great. So if there's no questions, let me keep going. So let me describe Lipton's proof of the average case hardness of the permanent of a random matrix. This is a classic result in complexity theory due to Dick Lipton from the early 90s. A very beautiful result, very simple but clever result. So I guess the starting point is that the permanent of an n by n matrix is sharp p hard in the worst case, right? That's a famous result in complexity theory due to Leslie Valiant, which says that essentially if I can compute the permanent of an n by n matrix for any matrix, say over a sufficiently large finite field, then I can compute the number of satisfying assignments to a Boolean formula, which is a hard problem. Now, how do we boost this worst case hardness to the stronger notion of average case hardness, right? So to do that, we'll use a simple algebraic property of the permanent, which is that it's a degree n polynomial in n squared variables. The n squared variables here are, of course, the n by n matrix elements. The matrix entries. All right, so here's the setting of average case hardness. We want to compute the permanent of our favorite worst case matrix X over our field, some arbitrary matrix. But we only have access to a faulty algorithm O that correctly computes most permanents over the field. In other words, this is what O does. It takes as input a random matrix Y, and its output agrees with the permanent with probability 1 minus 1 over poly over the choice of matrix. But for 1 over poly fraction of the matrices Y, the output of O could be completely uncorrelated with the permanent. Okay, so how are we going to use this faulty average case algorithm O to correctly compute the permanent of our favorite worst case matrix? Well, this is what Lipton does. It's sort of a polynomial extrapolation idea. We're going to choose n plus 1 fixed non-zero points in our field. We'll call them T1, T2 through Tn plus 1, and then a uniformly random matrix R in the field. And then we'll consider the line A of t, which is x plus t times r, right? So we take our worst case matrix X that we want to know the permanent of, we shift it by something random. Now there's sort of two simple observations, which once we're done, once we say them, they essentially spell out how the proof should go, right? The first is what we call the marginal property, which says if we look at each ti individually, well, A of ti is a uniformly random matrix over our field. It's because we took a fixed matrix and we shifted it by something random. And so what we got is a uniformly random matrix over our field. And the second observation is that there's this univariate polynomial property lurking here, which is that the permanent of A of t is a degree n polynomial in the single variable t. And of course, this is inherited from the algebraic property of the permanent, which says the permanent itself is a polynomial of degree n. All right, so now we're essentially ready to see how the proof works, right? The point is, by the fundamental theorem of algebra, this permanent of A of t is a degree n polynomial. And so these n plus 1 evaluation points, permanent of A of t1, permanent of A of t2, and so on, right, uniquely define the polynomial. So we can use polynomial extrapolation techniques to recover the coefficients of the polynomial, permanent of A of t, from these n plus 1 evaluation points. And then once we have that, it's trivial to see how to get back the permanent of x. We simply evaluate our polynomial at t equals 0, because when t is equal to 0, well, a of 0 is equal to x, and so the permanent of A of 0 is equal to the permanent of x. Okay, so this is how Lipton's proof works. Let me again stop briefly for questions in case you have them.
In observation 1, you're saying that it's uniformly random.
Yes, absolutely.
And there is one question in the Q&A. I'll just read it. It says, is there any reason for the average case complexity you've used of Lipton?
Yeah, because we're going to adapt it in a moment for random circuits. I hope I understood that question correctly. Anything else? Okay, great. So let me continue. So how are we going to adapt Lipton's proof from the hardness of the permanent, right, the permanent of a random matrix, to the output probability of a random quantum circuit? Well, like I said before, in many ways, I think these two quantities, the permanent and the output probabilities, are sort of similar mathematically. In particular, they both have this similar algebraic property. So much like the permanent, the output probability of a random quantum circuit has polynomial structure. So to see this, let's consider breaking apart our circuit into its gates. So let's say C is equal to Cm times Cm minus 1, and so on. These are, say, 2-qubit gates. Well, then the polynomial structure comes from the Feynman path integral, which allows us to write the output amplitude of the circuit as this enormous sum over exponentially many paths. But the value of each path is the product of m gate entries. So it's a very manageable quantity. And so not surprisingly, this is a polynomial of degree m in the gate entries of the circuit, right? And by the Born rule, the output probability, what we care about, P0 of C, is a polynomial of degree 2m. We just square the amplitude. Okay, so how can we use this polynomial structure to sort of adapt Lipton's proof in this new setting of the output probability of a quantum circuit? Here's one idea. It won't quite work, but it's very close to working. So let's say we choose and fix m Haar-random 2-qubit gates. We'll call those big H, H1, big H2, and so on. And now let's consider a new circuit, C prime, which is sort of a scrambled circuit. So, what we're going to do is we're going to take each gate in the worst case circuit that we want to know the output probability of, we'll call that Ci, and multiply by Hi, the ith gate of this Haar-random, this Haar-random ensemble that I made. And we'll notice that by the invariance property of the Haar measure, we've taken a fixed gate and multiplied it by something Haar-random, and so the output is completely Haar-random, right? And of course, this is the sort of the analog of Lipton's marginal property, right? Remember, Lipton in his proof took a fixed matrix X and shifted it by something random to get a new sort of uniformly random matrix. That's very much the equivalent of what we're doing here. We're taking a fixed circuit and we're shifting it, so to speak, by multiplying it by a Haar-random gate. But the sort of problem here is that unlike in Lipton's case, we've sort of scrambled too well. There's no univariate polynomial structure that allows us to connect the worst case circuit C with the scrambled circuit C prime. This new scrambled circuit C prime is completely independent of where we started, completely independent of C. So it's not at all clear how to do something clever to extract the output probability of C from output probabilities of C prime. Okay. So we need something a little bit more. And to do that, we'll do something we call correlating via quantumness. So we're trying to find the analog of Lipton's univariate polynomial structure, which allowed him to essentially extract structure out of randomness. Right, and the main idea that we propose to do this is to implement a tiny fraction of these 2-qubit Haar-random gates, Hi inverse. In other words, here's the new way we're going to scramble. We'll let the ith gate of the scrambled circuit, Ci prime, be Ci, that's the ith gate of the worst case circuit, times Hi, again, the ith Haar-random gate, times e to, so far that's the same thing as what we did before, right? And that didn't work. So the new thing here is we're going to multiply by e to the minus I little hi theta, where little hi is the log of big Hi, and theta we think of as something that's non-zero but tiny, very small. And the point is that this has a Lipton-like structure to it, right? If theta is equal to 1, right? Then, so if theta is not small, if it's equal to 1, then the corresponding circuit C prime is exactly equal to our worst case circuit C. Why is that? Because if theta is equal to 1, we've just gone and implemented HI inverse, and HI times HI inverse is the identity. So we get back that each of these gates CI prime is equal to CI. So we, again, recover our worst case circuit C. But if theta is really tiny, then each gate is close to Haar random. It's close to Haar random because if theta is really tiny, we've done essentially nothing, right? And so the circuit ensemble should be essentially random. So now we can try to use a similar proof structure. What we would do, just like in Lipton, we would take several non-zero but small angles theta, and apply polynomial extrapolation. So in other words, what you would do is fix, theta 1, theta 2 through theta m plus 1, right? Because the degree of the polynomial is m. And what you would do then is compute the output probabilities of these sort of scrambled but correlated circuits and use some sort of polynomial extrapolation argument to recover the output probability of the worst case circuit C. Now, this is very close to working, but it's not quite right. And it's not quite right for a very simple reason, which is that this quantity, this circuit, e to the minus, this gate, e to the minus I hi theta, it's not a fixed degree polynomial in theta. And so the solution that we proposed, which is a bit subtle, I think, is to take the fixed truncation of the Taylor series for e to the minus little hi theta. E to the minus I little hi theta. In other words, here's the final way we propose to scramble our circuits, which has sort of all of the properties to recover Lipton's style proof. So in other words, each gate in the scrambled circuit, C prime, is Ci times hi. Again, it's completely scrambled. But now instead of implementing e to the minus I hi theta itself, we'll implement the kth order Taylor series truncation of this gate, okay? And now it has what we want. So why is that? Well, because each gate entry is a polynomial in theta, because the Taylor series is a polynomial in theta. And then by the Feynman path integral, right, so is the output probability of this truncated circuit, C prime. Right, so now we can do exactly what I suggested before. We can use a Lipton style argument. We fix m plus 1 small thetas. And then extrapolate to recover the polynomial in theta, q of theta, and then compute the theta at 1, which, by the way we've set things up, is equal to the output probability of our worst case quantum circuit C. Okay, before I go on, let me take any questions. Okay, no questions about our proof here.
There's a question, how do you take this capital K?
I assume that means how do you set, like, how large should capital K be? And it should just be some polynomial. You fix it. Okay, great. So let me go on. So the subtlety here is sort of to motivate these truncations, right? Let's sort of think about what we did. What we did here is we introduced these Taylor series truncations to get some polynomial structure that allowed us to use a Lipton style of argument to show the hardness of the average case hardness of computing the output probability of these circuits. But in so doing, we changed the distribution over circuits. And in fact, this new distribution over truncated circuits is supported over circuits that are actually slightly non-uniform. They're non-uniform because we took the Taylor series and we truncated it, right? But so how do we motivate this? How do we motivate showing this hardness result for a different distribution over truncated circuits? Well, the key is to remember back to the Stockmaier reduction. In other words, our goal was not to prove the hardness of exactly computing the output probability P0 of C, but rather in computing a good additive estimate to within imprecision 1 over 2 to the n. Again, because the goal was never to prove hardness of computing, it was to prove hardness of sampling. And this was the error that was lost when we sort of went from one to the other. And so what our result is proving is it's proving the hardness of computing the output probability of a slightly non-unitary truncated circuit, P0 of C prime, which is nonetheless extremely close, like exponential in K, close to the output probability of the original circuit C. And so what I see as our main sort of technical result from this 2018 paper sort of motivated the truncations as follows. What we prove is that with respect to this additive estimation, this order of 1 over 2 to the n additive estimation, well, estimating the output probability of the truncated circuit is hard if and only if estimating the output probability to the same imprecision of P0 of C, the original unitary random circuit, is hard. So in other words, while strictly speaking, there's this small difference between the truncated circuit distribution and the original sort of unitary distribution, what we show is from the perspective of hardness of sampling, right? There's no difference at all. Okay, so that's sort of how we motivated this. And intuitively, because the truncation error that we're sort of making when we truncate the Taylor series at a fixed kth order is so much smaller than the size of the additive error where conjecturing is hard. If you look at my interval picture, what we're doing here is showing hardness here at P0 of C prime. That's the output probability of the truncated circuit. It's exponentially close, to P0 of C, the output probability of the unitary random circuit. But then we're making this conjecture that outputting anything in this much wider subinterval of width 2 to the minus n over poly is sharp P hard. And our result is saying, look, if we're going to make this conjecture, it shouldn't really matter if we're starting at P0, if the center of the interval is P0 of C, or very slightly close to it at P0 of C prime. And we've formalized this in our proof. But one thing that we did, technically speaking, is we left open the hardness of exactly computing the output probability of the unitary random circuit C. And this was filled in subsequent work by Ramis Movesag in 2019 and 2020, who sort of adapted our proof strategy, still used a sort of Lipton style extrapolation argument to go from an average case to a worst case and so on, but does so in a different way that sort of maintains unitarity when he's extrapolating. So he never has to leave the unitary group when he's going from his average case, when he's extrapolating between his average case circuit, the random circuit, and the worst case circuit. Okay. Once more, any questions about these results? Great. So now we've reached 2021. And in our recent paper, we've been able to improve the robustness of these results to additive imprecision, to greater additive imprecision. So, and one thing I'll say right away is that this same result was also obtained independently by simultaneous work of Kondo, Mori, and Movesag. So here's the theorem, just to remind you what I claimed earlier. So I claimed it's sharp P hard to output an additive estimate to P0 of C for a random circuit C to within imprecision 2 to the minus m log m. Right, so this is an exponential improvement over what was known before, which was on the order of 2 to the minus O of m cubed. Okay, so now let me tell you the main technical lemma that allows us to conclude that. Here's sort of the setting. Okay, we're given as input a certain sort of description of a polynomial, of a real polynomial of a single variable q of theta of degree m. But we're not given a sort of a typical description, like, we're not given, for example, the coefficients of this polynomial. Instead, we're given on the order of m squared sort of faulty evaluation points to this polynomial, where these points are sort of equally spaced in some narrow subinterval of the unit interval 0, 1, which we call 0 beta. I'm going to think about beta as like around 1 over m, the degree. And we know, and another thing that we know about these points is that at least 2/3 of them are delta close to the evaluation of the polynomial, right? So in other words, graphically, it sort of looks like this. There's this polynomial Q of theta, which is maybe this black curve here, right? But we're not given it explicitly as input. Instead, what we're given are these sort of faulty evaluation points, these red dots here. And what we're promised is that, most of these evaluation points should sort of hug the curve to within, they're delta close to the evaluation of the polynomial, the black curve. But then 1/3 of the points, like these 3 points out here, are completely off, right? They're not even necessarily correlated with the polynomial. And what we show is that using these faulty points, right, there's an algorithm. It uses an NP oracle, so it's strictly speaking not efficient. But what it does is it outputs Z, which is an additive estimate to the evaluation of the polynomial at 1, way over here at 1, to within imprecision delta times 2 to the O of m log beta inverse, where because of our setting of beta, beta is equal to 1 over m. So this is delta times 2 to the O of m log m with high probability. Okay, so in other words, what this algorithm does is something like this. It's going to output another polynomial. It's this blue polynomial. The guarantee we'll have about this blue polynomial is that it will agree with a potentially different 2/3 of these red points. And what we show is no matter how this polynomial is outputted by the algorithm, we show that the evaluation of this polynomial at 1 is sufficiently close to the evaluation of the original polynomial, this black curve at 1. And I'll say this is an exponential improvement over prior work in the following sense, in terms of beta. So the prior work had a linear dependence in the exponent in terms of beta, and we improve it to this logarithmic dependence, again, in the exponent. And so the upshot of this is that if delta is small enough, right, if these good points are sufficiently close to our polynomial, then what this is saying is that, if the delta, for example, is on the order of 1 over 2 to the m log m, we can use these faulty evaluation points to estimate Q of 1, the polynomial at 1, which is a hard problem. It's a hard problem because we think back to our prior construction, and we've encoded the output probability of our worst case circuit C in Q of 1. So that's a hard problem. And what we're saying is even computing these faulty evaluations, right, as long as delta is sufficiently small, like 1 over 2 to the m log m, is as hard as computing the worst case point, which is sharp P hard. Okay, again, let me stop and just make sure if there's any questions, please ask them.
So the bad points can be chosen, the value can be chosen adversarially, right?
Right, exactly. Okay, so so maybe we should, well, okay, maybe I can maybe wait for 1 more minute just to see if any questions are sort of materialize here. Okay, great. So then if there's no questions, let me keep going. So far in our discussion, we've talked about the hardness of imprecision, right? But not of physical noise. And physical noise is very important, of course, for a near-term quantum experiment, because we know that without error correction, the noise eventually overwhelms the signal. Right. So, for example, in Google's random circuit sampling experiment that they did on 53 qubits, they estimated that their fidelity was something like 0.2% and 99.8% noise, with every indication that if they made their system size larger, the noise would continue to overwhelm and the fidelity would be suppressed exponentially. And so, there's this really interesting question, which is how can we model this sort of uncorrected near-term noise from a theoretical standpoint for random quantum circuits? Well, one way to do this is by considering a fixed noise model, a fixed physical noise model. So for example, with respect to Google's ensemble of random quantum circuits, a very natural sort of modeling of their noise is to have each random gate of our random quantum circuit, CI, followed by a 2-qubit depolarizing noise channel. So this is this EI here is the depolarizing noise channel on 2 qubits with, say, some noise strength gamma, which we think of as some small constant. Okay. So another way of thinking about this is we can think about choosing a noisy random circuit by first picking our ideal gates in the circuit. So just like we did before in the noiseless case, these are CM -1, and so on from the random circuit distribution. So for example, maybe these gates CI are Haar random 2-qubit gates. And then the environment, or something that's not up to us, chooses the noise operators n from a distribution I'll call script n, which is specified by the channel. So for example, to be clear about this, in the case of 2-qubit depolarizing noise, these operators n are sort of uniformly chosen 2-qubit poly operators. Right. And then at the end of the day, when we measure our random quantum circuit, we get a sample, all n qubits. We get a sample from the output distribution of what I'm calling n.c. By this, I mean sort of an abusive notation. Dot here is gate-wise multiplication of the ideal gates in the circuit by the noise operators. Without ever learning what the noise operators are, right? So this is sort of the traditional sense that we talk about noise in sort of an error correction scenario, sort of an unheralded sense where you never learn, the identity of the noise operators. And so the point of this, which I think turns out to be quite interesting, is that very similar hardness arguments that worked in the noiseless case actually work almost directly here in the noisy case. And the point is, by the linearity of the noise channels, we can write the output probability of the noisy random circuit as this expectation value. We're essentially averaging over the identity of the noise operators of the output probability of the joint circuit n.c. Right? Or written another way, we're writing this as the expectation over n of the output probability of this of p0 of n.c. And the key point here, which is really quite simple, is that this can be written as a weighted sum of Feynman path integrals, right? I'm just writing out what this expectation value is. It's a larger, more complicated sum than the noiseless case. But the key point is that the property that we wanted to establish our worst to average case reduction still exists here, which is that this is a polynomial of degree 2m in the ideal gate entries. So we still have this polynomial structure. And so by essentially the same arguments as we sketched before, we can prove a worst to average case reduction over the ideal random gates C for computing the output probability of this noisy random quantum circuit to within the same imprecision, to within 2 to the minus O of m log m. Okay. Now this is just a worst to average case reduction over the ideal gates in the circuit. So the interesting question, another interesting question is, how hard is the worst case of this quantity, right? And to show that this is hard, that computing the output probability of a noisy quantum circuit is hard in the worst case, right? We can rely on a nice result of Fuji, who shows that this quantity is also sharp p hard to compute in the worst case, providing that the noise rate gamma is some sufficiently small constant. So as long as it's a constant that, that in other words, it doesn't depend on the number of qubits n, but in general, it would depend on the architecture of the random quantum circuits. Right, so we actually have hardness here in the noisy case. And I think the key reason I'm so interested in this result is for the following reason, okay? In the noisy case, unlike in the noiseless case, there's also a trivial classical algorithm for computing output probabilities. And the issue is quite intuitive. It's that, if we have uncorrected depolarizing noise in our circuit, where, we keep alternating layers of random gates with depolarizing noise and we don't correct, well, that's going to cause our output distribution to rapidly converge to uniform as the system size grows. It's intuitive. It's just saying that, if you have this depolarizing noise and it's not being corrected, you're adding entropy into your system. And eventually, if you keep doing this without correcting for your noise, you're going to reach the maximally mixed state or the uniform distribution. And as I always like to say in my talks, it's clearly not hard to output a probability from the uniform distribution. Even I can do this. It's 1 over 2 to the n, right? And so the really interesting question is, how accurate is this trivial algorithm that is supposed to give an estimate to the output probability of the noisy random quantum circuit? That trivial algorithm just outputs 1 over 2 to the n. Well, we don't know. We've been working on this in my group very intensely, but there's sort of a conjecture which appeared in the context of the Google experiment. So what Google conjectures is, for random circuits, this trivial estimate succeeds, or rather works with imprecision 2 to the minus O of m. Or by the way, this big O is hiding the noise strength, okay, gamma, which is some small constant. And in fact, we thought a lot about this. We can prove it in certain sort of simplified toy models of random circuits that this convergence is this fast. But I think the reason I think this is so important is as follows. I claim that this sort of provides a noise barrier toward improving these hardness results to any further precision, any better precision. Why is that? Well, what have we really done here? What have we accomplished? So let's recall. So on the one hand, in sort of the first half of the talk, we established that computing the output probabilities of a noisy random quantum circuit of size m is hard to within imprecision 2 to the minus m log m. Okay, these were our new results. But then on the other hand, we think it's classically easy to solve this problem trivially within imprecision 2 to the minus O of m. Okay, so what this is saying is that in the noisy case, the hardness result is essentially tight. You can't hope to improve this hardness result more than by a log m factor in the exponent, since we have easiness at imprecision 2 to the minus O of m. So the upshot here, which I think is relevant even to the noiseless case, it's especially relevant to the noiseless case, is that if we want to dramatically improve this robustness in the noiseless case, say to get a hardness of sampling result, to make this 2 to the minus n, the number of qubits, well, we need to invent new proof techniques that are not robust to noise, right? The fact that the same proof techniques worked in the noisy case as the noiseless case is a problem, because we know that the noisy case cannot be extended much further. And so, we need to find genuinely new techniques that are not robust to noise if we want to improve these results essentially any further. Okay, great. So let me conclude. So what have we done? We've improved the imprecision to additive error of computing the output probability of a random circuit of size m to additive error 2 to the minus O of m log m. Now, what we showed is that this hardness remains if the circuit is noisy. But in this case, we think that the same imprecision is essentially tight, up to a log m factor in the exponent. Okay? And so as a consequence, even though it seems like we're getting closer and closer to the imprecision that we would need to settle the quantum supremacy conjecture and improve hardness of sampling of a random circuit, we think that to get essentially any further, we'll need dramatically new ideas, dramatically new proof techniques. Thanks a lot. Let me take questions.
Yeah, any quick questions before we move on?
Looks like there's a question in the chat, which is, for boson sampling, would your argument about noise be the same as the case of Google depolarizing noise, or would it be different for boson sampling? That's a great question. The answer is it would be very different. Depolarizing noise is a good model, it turns out, for Google's experiment. In fact, if you read their experiment, they're very clear about this, that they really think a very good noise model is this sort of local depolarizing noise. But for boson sampling, it's really not the right model. For example, in most boson sampling experiments, by far the predominant source of noise is photon loss, right? And we're actually, we're studying sort of equivalent phenomenons in the case of photon loss. How quickly do you converge to something trivial, like say the vacuum state? Right? Strictly speaking, we don't know, but we're sort of hoping to show similar style results, that it should be sort of exponential in some parameter that's meaningful to the experiment. Great. Anything else?
Okay, so let's thank Bill very much. And our next speaker is Nicholas Hundred.